Red dwarfs. Red dwarfs are just suns in their main sequence. They are just doing the thermonuclear synthesis. They are just doing the stellar nuclear synthesis, the thermonuclear reactions. Inside of them, it is warm and hot because the pressure is pressing together, and the two hydrogen are overcoming, because they're so hot, their electrostatic repulsion. They're sticking together, forming helium. Red dwarfs are much smaller, and therefore this gravitational pressure, which makes the heat in them and so on, is much smaller, and this happens much slower. Therefore, they are not so bright. They have less luminosity, they have less mass, therefore less gravity, and also a smaller diameter. So they're much smaller, less bright. Inside of them, this stellar nuclear synthesis, two hydrogen pressing together to become helium, is not happening so fast. And another reason is the heat rises up and then cools down and it goes down again. So the hydrogen from the outside is also used up. In a bigger star, where the hydrogen at the outside is almost never used. It's just in the center at one time all used up. When it goes a bit together, and when it goes together, some hydrogen is, because the gravity is still so strong, but in the middle is now, the thermonuclear synthesis is no longer happening, because there's no hydrogen anymore used up, and it goes together. And there's no pressure to the outside through this stellar nuclear synthesis, and it collapses basically. When it collapses, some hydrogen comes again into the center, enough pressure, new one, it expands and so on. But basically, most hydrogen is never used up in bigger stars. Red dwarfs use it all up. The heat goes up and cools down and sinks again down, and the hydrogen, basically the whole thing is churned through completely, and all the hydrogen of a red dwarf is used up. And that makes it that such a red dwarf, for example, Proxima Centauri, lives 1,000 times as long as the Sun, which is 300 times as long as the universe is existing. A trillion years, what would it be? Now, so red dwarfs, there that happens much slower because they have much less pressure. And they are not so bright. Proxima Centauri is the closest one to the Earth. It cannot be seen with the naked eye. It is 100 times too faint to be seen with the naked eye from Earth. 80% of stars out there are red dwarfs, or 80% of the stars closest to the Sun are red dwarfs. And no one can be seen because we're too faint. Because inside of them the pressure is too low, because we're too small, the hydrogen is pressing not so fast together, not so much luminosity. That is according to Mark A. Garlick's Cosmic Planetary book on page 40 and 41. If you click this video at one point away, then please tell me what the reason was so that I can improve. Otherwise, hi and welcome. I am trying to learn Helio science today, red dwarfs, and after we've done that, we're gonna do wrist training. And if you participate in the wrist training, then it's at your own risk. Red dwarfs, feeble and faint. Feeble and feeble, I still don't know what's pronounced. Either feeble or feeble. So, red dwarfs. Main sequence stars are known as dwarfs, which does not mean they are small. It is simply that more evolved stars tend to be bigger. Okay, red dwarfs, they are in the main sequence. So the main sequence of a star, we are halfway through. The main sequence is the one where we are doing the nuclear fusion. The hydrogen in it fuses together to become helium. That pushes an outward force to the outside, and that thing makes the nuclear power in it, and that thing makes it burning. I don't get it. But it happens only because it's so hot and because the pressure is so strong. Hydrogen is pressed together, forms helium. And that is somehow how the Sun works, or stars, in the main sequence. Red dwarfs seem to be also stars in the main sequence, just that they are smaller. Red dwarf stars, however, are deserving of the term, having only a fraction of the Sun's mass, diameter and luminosity. So dim are they that not one is visible to the naked eye. The nearest Proxima Centauri is 100 times too faint to spot. Proxima Centauri is a red dwarf. Okay, something else. They are much smaller. They have much less mass. They have a much smaller diameter, so actually much smaller. And the luminosity, so how bright they are, is much smaller. And they are so much less bright than other stars that from the Earth no human can see just with their eye such a red dwarf. The nearest red dwarf to the Earth is Proxima Centauri, but it is 100 times too faint to be seen by people on the Earth by the eye. Red dwarfs have such a puny mass that the pressure at their centers from the weight of the rest of the star is relatively low. Ergo, these stars do not need to generate much energy to prevent gravitational collapse. So they consume the hydrogen stockpiles sedately. I don't know what sedately is. Does it mean it's like a sedative, like sleeping? In the meaning of slowly. Okay, they are much smaller, so they're having not so much pressure from the outside, so their gravitational collapse is not happening. We haven't heard what it is. And the nuclear fusion in it, so forming the hydrogen into the helium, doesn't have to be so strong. By this fusion, there's an outward force happening, putting the gravitational force pulling it together, and the outward force from this fusion of hydrogen into helium into an equilibrium so that it's balanced. And that prevents the gravitational collapse. They don't have to have it so strong because they wouldn't have anyway so early a high gravitational collapse, but that's not really a reasoning for that cause. But they consume the hydrogen stockpiles sedately. In addition, red dwarf interiors are fully or mostly convective. I don't know what convective means. Like pans of boiling water. Okay, I don't understand. The heat generated in the core rises to the surface, where it spreads out, cools, and sinks down to be reheated. So that's meant to mean like in water. That happens actually by boiling the water. The surface water, so the water is high, the water in the ground gets high. And when it rises up to the top, then it cools down, if it's not evaporating, and sinks again down. Do we say it here? The heat generated in the core rises to the surface, where it spreads out, cools, and sinks down to be reheated. But not the heat itself, the material. Basically, red dwarfs are like huge convection heaters. I don't know what a convection is, or a convection heater, with thoroughly churned and mixed interior gases. Does churning mean turn it around? Is that the meaning of churning? If there's a cooking book and it says you should churn the food, does it mean you should turn it around? We had it in gastroenterology in a part about the digestive system, where it was said in the stomach the food is churned. Does it mean it's mixed? So red dwarfs are like huge convector heaters which are thoroughly churned and mixed interior gases. In a sun-like star, by contrast, the gases higher up do not mingle with those in the core. Once a sun-like star exhausts its core hydrogen, the rest of the hydrogen higher up remains largely untouched, like a campfire that burns in the middle and leaves the edges unscathed. Why is that happening? Why is the hydrogen not used? I understand the analogy or whatever word is a campfire. There are people making campfires and they're taking the, whatever they call the pieces of wood, and they're putting them all together in a circle around it, all like that, and then they're making the fire in the middle. And the idea is that now the fire burns in the middle and inflames these wood pieces at the beginning, and then very slowly it burns to the outside over hours, so the campfire is burning basically the whole night. But it most of the times doesn't go completely to the end. It stops when the end pieces are not completely burned out. And this is now what is it? Now tutorial how to make a campfire. I don't know how it works with. Don't attempt it based on what I said. Now, once a sun-like star exhausts its core hydrogen, the rest of the hydrogen higher up remains largely untouched. But why is that happening? Because it does not sink down, but why is it not sinking down as with the other one? In a sun-like star, by contrast, the gases higher up do not mingle with those in the core. Why not? The heat generated in the core rises to the surface, where it spreads out, cools, and sinks down to be reheated. Okay, whatever. And the star doesn't use all the hydrogen in the outside. I heard that argument a couple of times. If a star would use all the hydrogen, they could burn much longer, but they're using just the one. I think I heard it somewhere. Inside a red dwarf, even hydrogen on the surface is transported to the core, where it is consumed during the main sequence. This combination of a slow fusion rate and a large hydrogen supply means that a star like Proxima Centauri is expected to be on the main sequence for an astonishing 4 trillion years. That's 290 times the age of the universe. So they're much smaller, have much more size, have much more mass, have much less luminosity, but still they burn much longer. Because they are burning all the hydrogen up which they have. The sun is not burning up the one on the outside. And also they're burning at a much lower rate. And so that thing can live 4 trillion years, that is 290 times longer than the universe is existing. And they're around something like 500 times longer than the sun can. Still, not even the stars are eternal. Once the hydrogen supply begins to run dry, replaced slowly and inexorably by a helium ash, the stage is set for the next phase in a star's evolution. Leaving the main sequence behind, it becomes a subgiant. So dim are they that not one is visible to the naked eye. The nearest Proxima Centauri is 100 times too faint to spot. Red dwarfs are the most common stars in the known cosmos. Of the 50 closest stars to the Sun, 40 are red dwarfs. Wait a second. Red dwarfs are the most common stars in the known cosmos. Of the 50 closest stars to the Sun, 40 are red dwarfs. This image shows a typical example. Fable and dim, the volcanic planet in close attention. What? This image shows a typical example. Fable and dim, the volcanic planet in close attendance. If you can make sense of it, finger. I wanted to say something. I forgot what it was. It was the thing. That means if human beings want to look into the sky and they see a lot of stars because we're not so close to cities, it is very starry night. That means for every star they see there are 4 or 5 other ones which are red giants. Because we have 5 or 4 or 5 times as often there are red stars than red dwarfs than normal stars. Okay, that was it. It was the Heliology part. If you were here for Heliology, you can go directly to the next part of Heliology, where we're going to do the part about the subgiants. If you stay here and participate in the Wristtraining, let's go to stable stance, hands next to the human body, and bring the fists down and up. That's the spotlight. And now the hand again, and to the inside and to the outside. And that is the flashlight. Now we're having 3 rules. The first rule is that we're stopping immediately as soon as there's pain. Next exercise, flip the hands into the inside of the magician. The second rule is that we go only as far as we can go with a little bit of effort. Now the pancake flipper, that hands up, down. And the third rule is that we're not overdoing it. We just want to strengthen, not to exhaust. Hands out and the T-Rex in the morning, down and up. Fists and them to the inside, up, outside. Again, down, outside, up, in. And now the hand to the side and down, press from the inside. Again, if there's pain at any time, then stop immediately. And we don't want to exhaust, just to strengthen, so don't overdo it. Pull from the outside. That is the crab anxious to a fever exercise. Press one top and pull it. Outside. Hand to fist, down, into flexion, press from the inside. On the outside, pull in. And both hands, down into flexion, down, up, and around, down, up, turn, turn around, down. last time. You can do this exercise way slower. Next exercise, the cautious big bang. Fingertips on one hand, open slowly, and close again. Other hand. The field takes its new symphysis jack. The fists open, close, flare and spread her fingers. Also with a little force. The T-Rex in the gym. You can use the tennis ball or do it without one. Make a strong fist or press onto the tennis ball. Release. Press. Release. Press. Release. Other side. Press. Release. Press. Release. And the next exercise, the Basco bridge. Flat fingers, flat hands together and up, and again together, and into the knuckles. Okay. The frog testing the water temperature. Hands next to the body and down with flat fingers. Again up, strong fist. If you need a break, take a break whenever you want. We just want to strengthen, not to exhaust. And if there's pain, then stop immediately. Again down and up. And now the claw fingers and claw them also with pleasure and try to bring the fingers outwards, spread them up and spreading, up and spreading, up and one side, and hands into flexion, down into extension flat fingers, up, flexion, strong fist, down, extension flat fingers, in, and again out, extension flat fingers, and we're ending with in. Next exercise, the ice X. Flat hand, bend little knuckles, press on all four fingers. Other hand. Last exercise. The rocket launches booster pack. I don't know what the name is. I forgot the name. Fists and bring them into flexion, strong fists, and extension and flat fingers. And again, strong fist. And out. And in. And last time in. And we're ending with a blow. Go with moderate pressure over the middle part of the lower arm. And on the other side. This was the wrist training. Thank you very much and until next time.